Welcome once again. Spenta will continue with his second lecture on higher spin fields and Fermion-Boson duality in 2+1 dimensions.
So yesterday I gave you a sort of a brief survey of all the work that has been going on for the past couple of years in trying to understand weakly coupled higher spin theories in the context of gauge theories in 2+1 dimensions. I will give you the references at the end of my talk, so I apologize for not having done that till now. Okay, so today our main task is to compute a partition function, the limit of Rj, and I'll tell you exactly what we plan to do. So now we work on, we are in 2+1 dimensions, and the manifold we work on is S2, the two-dimensional sphere times S1, and the radius of S1 is 1 upon beta, I'm sorry, this beta, which is the inverse temperature. So we are looking at a finite temperature partition function on S2 cross S1. And the partition function formally is written like this. It's a little distance, right? Is e to the I, the action of Chern-Simons theory, plus I times matter, all types of matter possible. Like yesterday I described bosonic matter, fermionic matter, supersymmetric. Even in principle this can be calculated when you have the matter deformed away from theories deformed away from conformally invariant points. It's a little subtle. So in this talk I will not actually take that into account, but I will work with conformally invariant theories. Okay. All right. Now, so I forgot something. Stupid. Matter. There is a functional integral over matter fields, functional integral over the gauge fields, and the gauge group is UN, and the Chern-Simons action, which I had written down yesterday, is k upon 4 pi integral over S2 cross S1 trace of A dA plus 2/3 A cube. I think there's an I here because we work with Hermitian gauge fields. Okay, so now the point is that I want to split this path integral into an integration over the gauge field, which will have e to the I Chern-Simons, which is a functional of the gauge fields, times the integral over matter e to the I S matter, and S matter has matter fields but also has the gauge field. All right, we are at so I try to argue for you something that this problem is actually exactly soluble in the Lagrangian limit. So there will be a certain sequence of statements, don't stop me anywhere, but in about 5 minutes it will be very clear what are the approximations and the limits we will be working with. Okay, all right. So so let me also now define for you, since we are at finite temperature and we have a circle in our problem, it is possible to consider a gauge invariant operator, which is the holonomy of the third component integrated around the circle dx3, and over here small x will always mean element of S2. At each point on the sphere you can actually define this holonomy matrix. This is a n by n unitary matrix, also called the Polyakov line, Wilson loop, whatever. All right. And one of the most subtle questions that arises in trying to calculate this integral is the problem of gauge fixing, which I will be discussing with you. But for the moment, I will already fix a certain gauge which says that the third component of the gauge field is independent of x3. This is the nearest you can get to the axial gauge A3 equal to 0 because you are on a circle. So at least you have to admit finite connections on the circle. So this then becomes e to the I beta times A3, which is only a function of points on the sphere. Okay, so this is a definition. Now let's make some estimates of how to take the large n limit. You see, large n limit is mainly controlled by the degrees of freedom in the measure of the path integral. So over here you see that the degrees of freedom in the measure is n square, okay, because there are n square, because this is a n by n Hermitian matrix, so it has n square components, so it's n square. On the other hand, since we are working with vector matter, okay, the number of components is n. Okay. Now there is a lot of understanding about how these different measures interplay in various dimensions, but I will only use it to make a little estimate that this part of the path integral actually will go as something like exponential of n square. Okay. This is from the gauge field. This is very heuristic. I will revert to something more concrete later on. And this one will go something like exponential of n. But we know more about this path integral because, as I said, I am going to restrict to conformally invariant theory. So therefore, I would expect actually that it should go as the square of the temperature times the volume of the two sphere. And the point is about how you take these limits. If you took the volume to infinity first, you will actually miss this part completely. And this was the miss we had in our first paper actually on this subject, that we completely forgot about the holonomy of the gauge field because we took the volume going to infinity first. And this is a grave error. In fact, even the practitioners of the large n limit made because they know that n is the largest number in the problem, and so you've got to be very careful about the order of limits. Okay, having said that, this means basically that n square must be comparable to n t square v2 in order to have a sensible limit, and which means basically that I introduce a number psi to parameterize my theory so that t square v2 is equal to z times n. I will be working in this problem. We will evaluate this integral in the limit in which t square v2 upon n is held fixed, okay, for a given value of z, so that I have all the competing degrees of freedom and I can do a correct saddle point method. Okay. So this tells you now, because I'm working with a conformally invariant theory, I can just set v2 to 1 or some fixed number, whatever. So basically what this tells you is that t is proportional to square root of n, which means that the large n limit and the high temperature limit actually go together. They are synchronous, and this is the reason why we can solve this problem. Okay. So because of this, when I integrate over the matter at finite temperature, I know that the matter fields develop large thermal masses proportional to T square, and therefore they are very large precisely in this limit. And this is why when I integrate out matter, I don't want to explain all the diagrams to you, but you can see that every time there is a propagator of the matter field, it will have a large mass. The mass goes as T square, so as n, so you get a, you are guaranteed now to get a local action over here. This integral can be in general said to be local. It will be local in the holonomy field and the gauge fields on the sphere. So what can I write down? I'll just write down, yes.
So I can take T fixed and T2 goes like in that also, right?
Yeah, you can do that actually, but I'm not doing it that way. You can do that.
That would give the differential.
The T square V2 is some fixed object, and you can scale either T square or V2. I'm doing V2. Okay, so this tells me the following, that I can write the Z prime, which is, let me actually denote this part of the integral as Z prime. That is the integral over the matter fields. Will have an expansion something like this, n because vector matter, and then I have the following. So I have an integral over square root of g, where g is the metric on the sphere, times some function of the holonomy times t square. This is the first term by dimension analysis. Then I can have another term like v1 u, and now covariant derivative on the sphere of the holonomy matrix, covariant derivative, conjugate, etc., etc. Now it is very clear that in the Lagrangian limit, this is the dominant term basically, and all the other terms will sort of go away. In the Lagrangian limit, I have used this, I wrote this down just using dimension analysis. These are unknown functions which I have to calculate depending on the matter, and I have introduced t square just by dimension analysis, and no t square here because you have two derivatives, etc., etc. All right, so this is the type of local expansion you will have, and because of this particular type of limit that I am working with, I can drop all this in the n going to infinity limit, and z prime essentially is e to the minus t square n integral square root of g v of u of x d to x over the sphere. So this is a very important result. Now v depends upon the type of matter content, you know. You have some matter, you calculate it. In tomorrow's lecture I will tell you how to calculate this, because this is the most difficult part actually, means to really do, and that was done first before all these insights came around. That was okay. So now our problem is very interesting. We essentially have the following problem to solve. Our problem now is to look at an integration over the Chern-Simons, e to the I times the Chern-Simons, and times e to the minus t square n, the integral of the holonomy matrix. Okay. All right. Now, very nice. So what I can do is, this obviously is the partition function of the pure Chern-Simons theory. I multiply and divide, okay. So then this just becomes the expectation value of e to the minus t square n of this animal. Sorry, it's not an animal. And the Chern-Simons theory is characterized by the rank of the gauge group and the level K of the Chern-Simons theory. So this is the result, that the partition function is exactly equal, the thermal partition function is exactly equal to the average of some functional of the holonomy in the pure Chern-Simons theory. Okay, so this is the result. Now this is a very powerful result actually, because now Chern-Simons theory has been sort of beaten to death, and by physicists, mathematicians, there are lots of interesting results, and one of the important results which I will now use is what is called level rank duality. So now we will now study the symmetry properties of this partition function. The computation of V we will postpone. So what can we say about this? Okay. So the first thing I would like to say is that Chern-Simons theory is a topological theory. So clearly this answer cannot depend upon the metric of the sphere, or for that matter metric of any manifold of 2 dimensions. What I am saying actually is sort of valid for any Riemann surface in 2 dimensions. It can also not depend upon the position, because it's a topological theory. Okay. So this means the following, that this is equal to Z Chern-Simons, which I will normalize to 1 basically, okay, and expectation value of e to the minus t square n times the volume times V of u, where u is nothing but the 0 mode of the holonomy matrix on the sphere. No x dependence, it's gone. Okay. So this is a beautiful result, that this partition function is given essentially by a Chern-Simons theory with this type of an operator introduced. All right. So this is some function on the unitary group, okay, V of u. Now any function, any invariant function on the unitary group has an expansion in terms of the characters of the unitary group, right? So let's do that. So now let's calculate, let's try to make some statements about the properties of this fellow. All right. So I said that if you take e to the minus n t square v2 v of u, this can be expanded in terms of the characters, some depends on square beta. It's sort of obvious thing I have written. You can expand any function on the unitary group in terms of the characters which form a complete set. Over here, y denotes the sum of all representations. So y denotes the Young tableau. Of UN representation. Don't worry about what it all means. Young tableau, you know what it means. It's something like this. And you know, it has a certain number of boxes in the columns and the rows, and well, this is all related to representation theory of unitary group. Okay, this is true. So therefore, this expectation value is this expectation value, right? So we want to make statements now about the expectation value of the character of the unitary group given by the Young tableau, and the number of boxes of this Young tableau I will call small n. Okay. So now there is a formula due to Schur which tells you how to write the character in terms of the Wilson loops or the Polyakov line. And this is not all very surprising, but Schur lived in the 19th century, I think. So but it's a beautiful thing. So let me write down. So the character at the point U, point means element of the unitary group in the representation y is given by 1 upon n factorial summation over all the elements of the permutation group Sn times this product to n trace of u of m power of m and this is from m equal to 1. All right. So this means the following, that this is given as a sum over the characters of the permutation group of order n, where n is the number of boxes of the Young tableau. Just note the statement of the result. And K1 up to Km up to Kn are the lengths of the cycles. K1, so many cycles of length 1, K2 cycles of length 2, Kn cycles of length n. So this all comes from the, none of this is necessary for what I am going to say actually in real stuff that we will do. Okay. So this is the Schur polynomial in terms of the Polyakov line. Now, when you talk about level rank duality, let me just tell you briefly what is the statement of level rank duality in Chern-Simon's theory, which is a known proved statement. Then we will use some theorem from group theory to make a very interesting statement about our partition function. Okay. All right. So shall I write here? Is it visible or shall I go there? Say something, somebody. Oh, you have another screen there. Ah, okay, okay. Yeah, that's real. That's progress. That's fine. Previously, in the past, we didn't have. Okay, good. So I will write here. So what is level rank duality? So it says the following, basically, that if you take the expectation value of the character in the representation y in a Chern-Simon's theory of rank n level k. Okay. So this object, this u is actually is integrated over. So please remember that this is an expectation value. There is an integral over a unitary matrix of un. So this is actually equal to then the expectation value of the character of a transposed Young tableau. I will tell you what that is. But the Chern-Simon's theory is of level mod k minus n minus k. And if we work with positive k's, this is just k minus n k. And what is this? Y twiddle is the transposition of the definition of transposition of the Young tableau is simply interchange the rows and columns. So here is a statement of level rank duality. It is not usually said this way, it is talked in terms of Wilson loops, but any Wilson loop can be expanded in terms of characters. So I just say it this way, that take a character of a certain representation given by Y. This expectation value in this theory is identical to the expectation value of another object. Y went to Y twiddle, okay, in another gauge theory given by this rank and this level. This is the statement of level rank duality. There's a history of this subject, and there's a lot of controversy about this history, so I won't get into it, except that recently there's a lot of nice papers by Kapustin and collaborators which actually have discussed this type of problem, and we learned from there precise statement about level rank duality. So I hope this is clear that this is level rank duality. Now arises a math problem. When I put chi of Y twiddle, what is on the right hand side? So that's a math problem. So this math problem was solved by consulting a mathematician, and he immediately knew the answer right away. That it's a well-known theorem in group theory that the character of the transposed Young tableau is the following. So this is the lemma, group theory. That chi of Y twiddle of U is equal to 1 upon n factorial summation again element of Sn, the character now Y of sigma, not Y twiddle but Y, and m equal to 1 to n minus 1 m plus 1 raise um to the power of km. Yeah. So it's very beautiful and it's very simple. So in fact the theorem is that chi for the permutation group, for an element of the permutation group, is nothing but the sign of G times. So for the permutation group, this is simple, and the sign of G is precisely given by this product, m equal to 1 to n, because there are n boxes in the Young tableau, and minus 1 to the power of m plus 1 raised to the km. All this math, what it means basically is the rule is that trace u to the m goes to this. So ultimately it is very simple that the character of Y twiddle is related to the character of Y in that gauge theory on the right hand side, okay, by this type of simple rule. Okay. So this is what it means.
We get some simple formula.
Sorry?
This right hand side I can go on and expand in terms of characters only.
Which right hand side? Where?
The expression of chi Y tilde of u.
Yes.
The right hand side is trace u in. This
Yeah.
I can.
So this character of Y twiddle is related to the character of Y in this particular way. The character of Y was given here, right?
Yes.
So if I put white here, how are the Wilson loops related? So you get a simple formula for the way the Wilson loops are related. That's what it says. Okay. So this is the statement of level rank duality in terms of the Wilson loops. So what it means is that our calculation of the e to the t square v2 times v of u at in k, if your v of u is such that this happens, if this is true, then two theories, you know, with VA and VB, or V twiddle I wrote, are related by level rank duality. So this is the point. So you essentially reduce the method of proof to prove the duality to this type of formula. And at the saddle point, it will just mean basically that this function will go into this function under certain transformations, which are come to later. Any questions, Sandeep? Yeah.
Sure. V tilde is defined as the analogous quantity to V, but computed in this k minus n k theory.
Yes, that's right. Yeah.
And then if this is true,
Right,
then
that's right.
thank you.
Okay, so this, I will end this discussion over here and continue with the calculation of the Chern-Simons path integral actually now. And tomorrow we will discuss how to compute, actually some scheme of how to compute V's for various theories, and then check the very strong people in the audience who have checked all these things. So, all right, okay. So, okay, I think I will finish. Okay. So now we want to calculate, really calculate this integral. Where u is the holonomy of one of these fellows. Okay? All right. So maybe, you know, before I show you the full calculation, and by the end of it you get all very tired, I will just tell you what the answer is first. The answer is the following. The answer is that it is a product of I equal to 1 to n. Summation over fluxes corresponding to each of the u1s of the un theory product of I not equal to 2 sine of mi minus mj upon 2 times e to the minus b. Surprising, but this is the answer. This is the answer for the sphere. Okay, this is very subtle to derive this. I will try to discuss with you how to solve this type of problem. But Blau and Thompson many years ago, using methods of algebraic geometry, actually computed this for arbitrary genus Riemann surface, and this is the answer. Okay. So we were very happy that our answer actually somehow matched the Blau-Thompson answer, which is absolutely correct. Okay, so for us, this is not there. So this is the answer. Now, how do I arrive at something like this? And after all, there's a continuum integral, and so the whole story is in the gauge fixing problem. So let me try to sort of delineate this issue. Okay. All right. So, any questions till now? Any questions? I mean, this is a sum over equally spaced integers actually over here. I think there's a mistake somewhere here. There should be a 2 pi upon k here. Yes. Yeah. That's just very important. All right. Okay. So let's try to justify this type of formula. Okay. Now, I already said that one gauge which I have fixed is this one. So I'm left with gauge transformations which are valued on the sphere. So what I do is that I take this holonomy matrix on the sphere and say that the gauge choice is such that it is diagonal, that is A3 ij at every point on the sphere is delta ij alpha I x, and I put this beta for normalization. And then once I fix this gauge, I will be left with u1 cross u1 cross u1 up to the n u1s of un. So I have to fix that also. So this is fixed essentially by introducing taking a I 1 x. So this is the zero mode. This is the zero mode of the gauge field A1 integrated over x3. So I will just write something like this here: x1 plus x2 this will fix the u1 Coulomb gauge. So all you are left with now is constant gauge transformations. Now, this is fine. Everybody knows you can do this. And this leads to a certain Faddeev-Popov determinant in the measure, which is just this one, right? But this gauge is very problematic. And I want to illustrate to you how it is in the understanding of the choice of this gauge that all those flux sectors arise and the integral actually reduces to a discrete sum. So I want to explain that in a simple example to you. Okay. So the understanding of what I'm going to say is not, I mean, many years ago, a couple of decades ago, 't Hooft actually discussed the problem of quark confinement in non-abelian gauge theories, and he used precisely this type of gauge, the so-called abelian projection. And he discussed how when the eigenvalues of this matrix actually start coinciding, you get monopole sectors. means topological defects. So when the eigenvalues coincide, there appears a topological defect, and those defects basically are magnetically charged under these residual U1s. He had monopoles because he was working in 3+1 dimensions. So we have to appropriately change the thinking in 2+1. But that's the sort of motivation, to think like that actually. Okay, so let's do SU2, simplest example to illustrate what I'm trying to say. So U of x is some SU2 matrix now. Okay, so I can diagonalize this matrix, right, like this. Okay, and the gauge fixing essentially means that you decompose the object you want to fix in terms of group variables, the symmetry variables, and the invariant coordinates actually, which are these angles. But there's a problem. This will fail whenever this diagonal matrix becomes 1 or -1. Then there is no gauge fixing. In some sense, they are coinciding up to a sign. So whenever this diagonal matrix is either 1 or -1 in SU2, then this gauge fixing fails. So what you would like to do is you would like to restrict this type of gauge fixing to the set of U's in which you remove +1 and -1. Okay. Look at this set and do your gauge fixing on this set now. So what is interesting is that this set is such that the maps from S2 into this set are topologically non-trivial, and they are classified by integer, and I will explain in a second why. Okay, so to explain means you give analogy, because in a 1-hour lecture it's very difficult to prove, but I'll come back to some sort of a proof later on, more physically. Okay. So think about the maps from a circle into S2. Okay, so this map is obviously trivial. However, if you remove these 2 points, the north pole and the south pole, from this manifold, then it essentially becomes a topologically a cylinder. And this map is non-trivial. It's very similar type of thinking in higher dimensions. If you excise points where the diagonal matrices become 1 or -1, then you pick up non-trivial topological sectors. Okay. So with this simple point, there's another way of looking at this problem actually, which is a little bit more prosaic, that the set of gauge transformations that you have over here is not unique. You can left multiply by another diagonal matrix over here and nothing will change. And if you mod out now SU2 by these diagonal matrices, you get a U1, and the maps from the sphere to SU2 mod U1 are also topologically non-trivial. So it's the same story actually. Okay. Now so what I'm trying to say now, as applied to our problem, is that e to the I A3 of x is basically this diagonal matrix e to the I alpha 1 upon beta, e to the I alpha 2 x upon beta, e to the I alpha n x over beta. Okay. And I will order these eigenvalues because there is a symmetry, permutation symmetry left over, the wild symmetry of UN enables me to sort of order these eigenvalues. And then I can discuss actually what will happen when this coincides with this. What will happen so that only the identity comes out, or -1. So exactly similar phenomena. So this means basically that the manifold over which I am integrating the holonomy matrix really splits up into domains. Okay, each domain is actually characterized by fluxes of the corresponding U1, which comes from where I am. And you will see that these are precisely the fluxes that arise on this S2 as we proceed. Another way of putting it in a very sort of, poor man's way of thinking is that if you have S2, you can have constant fluxes on that. Now there is no non-singular gauge field that will actually lead to that unless you have a Dirac string. Well, this is what this stuff is all about actually. If somebody is following me a little bit quickly, this is what this is. So this is a more precise and rigorous way of just saying that on a sphere I can sort of spread constant flux, and you will see that there is a term like that over here, and those fluxes exist precisely because I am taking into account singularities, Dirac type of singularities in the gauge fields, and you will also see that there's a very important factor of half actually which comes because of that, because the Dirac monopole has a half factor. Okay, all right, so I hope I'm getting across. I mean, you have any questions, please ask me at this time about this gauge fixing problem, because this is really very subtle and it's not totally trivial. So if you have any questions, please ask me, or maybe later on in the discussion I can answer.
Could you repeat what you said about the predicting frequency?
Yes. You see, if I fix this gauge, what are the gauge transformations on the sphere which leave this condition that this is diagonal, invariant? And those are precisely the residual abelian gauge transformations, U1 cross U1 cross. And those I fix essentially by a abelian Coulomb gauge, which has no ambiguity. Now what I said is that something much more is happening, that this integral actually is being broken up into various topological sectors which are characterized by fluxes, okay, which arise from the gauge fixing ambiguity in this theory. Okay, and they are related essentially to constant field strengths, constant abelian field strengths on the sphere. That's the summary. Okay, so let's move on. How much time do I have, Jano? How much? 10 minutes. Thank you. That will be fine. No, okay. A little bit more I can take, then I can actually finish something here. All right. So now let's get back to our calculation. So to remind you, we are computing this partition function, and this partition function can be split up into integrals over A3 because of the holonomy that is special in our case. In this direction, the Faddeev-Popov determinant because of this gauge fixing, e to the minus e square n v2, sorry, e square v2 u times the integration over dA1, integration over dA2, e to the minus sum of two actions. So all I'm doing is now splitting the Chern-Simons theory into integration over A3, which is special because of the holonomy, and the other two fields. And what I will do is that this is a Gaussian problem, and we will be able to do it. Subtle but doable, and that's what I'm going to do now. Okay, so here S1 turns out to be IK. I think I'll do the following. I'll switch to blackboard now because I don't need all this. Is equal to IK upon 4 pi. Okay. So this is what that integral is basically, and S1 and S2 I have defined over here. Now you notice actually that because this A3 is independent of X3, the X3 integral just comes here, and so these A1 and A2 that appear here are nothing but the zero modes of the gauge fields with respect to the circle. Okay, that's one thing. The other one, the other little point is that D3 essentially is equal to D3 plus I adjoint A3. By adjoint I mean acting by commutator on the right. Because this A3 is again diagonal and independent of X3, you will notice that certain components, the diagonal components AII, which are the zero modes of the diagonal components, don't appear here. Okay, this is just very elementary points. So taking all these little things into account, I will write A alpha of ij essentially as equal to this zero mode plus a twiddle ij of x alpha equal to 1 and 2. Okay, and this has a x3 over here. This is such that its integral over dx3 is equal to 0 because I have extracted out the zero mode over here. Okay, you do this and you plug in the fact that A3 is diagonal, and you get something recognizable and interesting. So S1 then turns out to be I times k upon 4 pi. You have an integral over S2, sum over I1 to capital N. The eigenvalues alpha Ix and D1 A2 minus D2 A1 I. So this is the abelian field strength I was talking about that corresponds to the residual U1s. It just comes out of the action and it's multiplied by these eigenvalues. Okay, so that's the first point. And I will elaborate upon this in a minute. Before that, let me say that this is a quadratic integral, but over vector spherical harmonics on S2. So you can do that actually. So the integral over IS2 A1 A2 turns out to be 1 upon the square root of the determinant with the zero modes removed of D3 plus adjoint A3 over vectors. Okay, so you can convert this into a determinant over scalars in an appropriate way by excluding the zero modes of the scalars. So this is all technical stuff, but I will come to that later. If somebody has a question, we'll discuss this. Okay, now let's get to this important piece actually, what it does. So it does the following. Okay. So there are two things to notice here. One is that if I have to admit a flux in this theory, these potentials must have string singularities. Okay? Otherwise, you cannot actually have non-zero flux in the sphere. So I, in some sense, in my mind actually, and also I can do it, separate the contribution of the fluxes from that of the regular gauge fields actually. Okay? So I do that. And then I write the regular gauge fields on a sphere. They can always be written like this in terms of a longitudinal piece and transverse piece. Okay? The regular vector fields are written this way. Then I know that there is a Coulomb gauge which has been fixed, right? That I've done. This implies a Laplace equation for this. It's obvious. If you impose this, this is what will happen because this term drops out. Laplacian on sphere, compact manifold, only solution is constant. Therefore, it just goes away from here. And all you're left with is these fellows over here. And so let's now try to evaluate this integral over here. So S1 is k upon 4 pi whatever. I won't be very careful with all this. And you have a sum over I, alpha I of x. And you get del square of chi I. If you substitute over here, you get just the Laplacian of chi I. Okay? Plus, of course, this is an integral over d2x plus I upon k or pi, whatever, and I alpha I of x times those f's which come out of the singular part of the gauge connection actually. So which this is proportional to a flux. Okay, so now very easy, you integrate by parts over here. So you remove this, you get a del square, and you can integrate over chi I because that's part of the integration. So this gives a delta function which says that the holonomy eigenvalues are constants. Exactly. So the holonomy eigenvalues are constants. It says that. So this comes out over here. So it's integral I. This is the flux. Now think in terms of the going to this diagonal gauge. This is a singular gauge transformation. So this gauge potential has a singularity, and that Dirac type singularity, and therefore the quantization is 4 pi, which is the area of the sphere, times integer divided by 2. This 2 is very important. You can't miss this 2. You don't get the right answer otherwise. And this is precisely the Dirac quantization condition. If you think in terms of your sphere, just imagine that there is, it's filled up inside, and there's some monopole here, and there's a string singularity. You want to compute some such object, you will essentially do a small Stokes theorem of the abelian gauge fields around this fellow. And the quantization condition is this one. All right. So it all fits in very well, that the topology of the gauge field functional integral produces fluxes which are precisely these, actually, integers which are precisely these. Okay, so now it's very nice. So this integral essentially e to the I times S1 is nothing but the following. If you put all factors and everything correctly, it is ik summation I equal to 1 to n alpha I mi. And this is for each u1. Okay, so you have to bear that into account. Now, if you have a formula like this in which you have to sum over all the fluxes, then I can use the Poisson summation formula, which is nothing but a statement of electric magnetic type of duality, and this is equal to I equal to minus infinity to plus infinity delta of alpha I minus 2 pi upon k mi. Okay. So this tells you why the path integral over the holonomy actually is not an integral anymore, but really a sum over these discrete fluxes. And that comes from this Poisson summation formula over here. And you know, 1 upon k is something like the magnetic charge. In that sense, I said it is electric magnetic duality type of thing. Okay, so this is a physical thing I wanted to talk about. Now I'll simply write down for you the answer for the measure of the other stuff. You know, we have this determinant, we have the Faddeev-Popov determinant, and so what is the ratio of the Faddeev-Popov determinant to the determinants over the vector fields? So this I will now write down the answer. In our understanding, this is a very complicated problem because you have to, because as you see, the sphere has fluxes, and doing determinants over fluxes is like working in monopole sectors, okay? And what is important is that the ratio of the determinants doesn't care about the fluxes. And that is not obvious to show at all, actually. And this is why the rigorous treatment of Blau and Thomson comes into play. I mean, this is not obvious at all why this happens. So all said and done, this this integrals, if you put everything together, you just get the answer which I sort of wrote down before, and I'll just write it again, that it is equal to I equal to 1 to n, and summation over all these fluxes, and then there is the determinants which very beautifully organize to give you sine of 2 pi upon k mi minus mj upon 2 v of with v2 t square and n. So this is the answer. So in all this discussion, the only thing I didn't really derive for you was the formula for the vector determinant in terms of the scalar determinants. Basically, you get the square, but you got to remove the zero modes, the scalar zero modes. And therefore, what happens fantastically is that this determinant ratio also becomes independent of the points of the sphere. See, that is why there is no sphere left anymore here. Just this flux. So this is the final answer. And I think, should I stop here now? Yeah, I think this is a good point to stop, because the next discussion we'll do tomorrow. So you have any quick questions? I am willing to answer, because I don't know how well I'm getting across really.
Let's thank Spenta and now open for questions.